All right, in section 13.6, we're looking at the binomial theorem. And the only thing that we want to talk about from this section is just the fact that that combination that we've been doing, here's that same formula that we've been using, that's the same thing as the binomial theorem. So another way that they might write that is they might write it with the n stacked on top of the r. All right, so for 13.7, we want to look at probability. So take a second, if you would please, and pause your computer and go ahead and read this paragraph about the different terminology. When you're looking for the probability of an event where all of the outcomes are equally likely to occur, your probability is just going to be the number of elements in the event over the total number of elements in the sample space. So we could abbreviate that in this way. Probability is always going to be a number between 0 and 1. You can use a decimal or a fraction. When your probability is equal to 0, that would be like if it's raining outside and we say, what's the chance of it not raining today? That probability is 0. That's an impossible event. Your probability is 1 when it's a certain event. So if it's raining outside and we said, what's the chance of it raining today? Then that would be a certain event with a probability of 1. All right, example number 1 says a 6-sided die is rolled. Find the probability of rolling an odd number. Okay, so first off, I need to figure out my denominator. What are the total number of elements in the sample space? Well, it's a 6-sided die, so that means that I have 6 different ways that die can land. Out of those, it says find the probability of getting an odd number. Well, on a die, 1, 3, and 5 are odd, so 3 out of the 6 sides, and we would always want to put that in our simplest form, 1 over 2. All right, look at the next one, a number greater than 4. So again, I still have 6 numbers to choose from, but how many of those are greater than 4? Just 5 and 6, right? So that would be 5 and 6 out of all 6 of them, and again, I'm going to put my answer in lowest terms. Now, the first formula that they give us here is the probability of finding A or B. They'll also sometimes write it with this symbol from geometry. That is a union symbol. So we could say the probability of A union B. But the formula is the probability of A plus the probability of B minus the probability of A intersected with B. Now, an intersection is exactly what it sounds like in driving. It's where 2 roads cross over each other. So the intersection of A and B is just where those 2 things overlap, where they cross over each other. So example 2 says a card is drawn from a standard deck. Find the probability of drawing a heart or a 7. Okay, so we're going to do probability of heart or 7. That's probability of heart plus probability of 7 minus probability of heart intersected with 7 from our formula above. Okay, so if you're drawing one card from a standard deck of 52 cards, your denominator is going to be 52, right? And what's the probability of heart? Well, there are 13 hearts in the deck of 52. Then probability of a 7. All right, well, out of the deck of 52, each suit has a 7. So there's a 7 of hearts, a 7 of clubs, a 7 of spades, a 7 of diamonds. So that's 4 out of 52. And then it says the probability of hearts intersected with diamonds. So are there any hearts intersected with 7s? Are there any hearts that are 7s? Well, yes, there's 1 7 of hearts. So I would subtract that off. Here's how that formula works. Right over here, did we count the 7 of hearts when we counted all 13 hearts? Yep. And did we count the 7 of hearts right here when we counted all 4 of the 7s? Yep. So that formula just took care of that redundancy. It subtracted it back off so we didn't count it twice. So we can say 13 plus 4 is 17, minus 1 is 16 out of 52, and then again, we're going to put our answer in lowest terms. All right, look at another one of those. So the next one says the probability of 6 or 7. That's the probability of 6 plus the probability of 7 minus the probability of 6 intersected with 7. All right, so again, I have 52 cards in my deck to choose from, and out of them there are 4 6s. There's 1 6 in each suit. And then similarly here, I have 52 cards to choose from, and there are 4 7s because there's 1 7 in each suit. So where do 6 and 7 intersect? Well, there's no way to have a card that is a 6 and a 7 at the same time. And so that would be 0. So we're going to have 4 plus 4 minus 0. That's going to give us 8 out of 52. And that would reduce down to 2 out of 13. Now, this probability right here of 6 intersecting with 7, 6 and 7 are called mutually exclusive events. They have no outcomes in common. They cannot coexist. And so anytime you have the probability of something mutually exclusive, that probability is always going to be 0, and it's going to drop out of your formula. While we're talking about mutually exclusive, there are all kinds of different scenarios that we could include with that. You are either a junior or a senior. You are either a Christian or a non-Christian. John 14:6 says, I am the way, the truth, and the life. No man comes to the Father except by me. And that was Jesus speaking. So only one way. All right, then the next formula that we have is the probability of A and B. So the probability of A and B can also be written as the probability of A intersected with B. That's the probability of A times the probability of B, and this line right here is read given. So the probability of B given A. So here's what they're saying. We're going to find the probability of A, and then we're going to find the probability of B if we know that A is already true. It's given that A is already in play. Okay, so for instance, example 3 says 2 cards are drawn from a standard deck. Find the probability the first card is red and the second card is a spade. And we're going to do this first one without replacement and the second one with replacement. So we've got the probability of red and a spade. So according to our formula up above, that's going to be the probability of a red times the probability of a spade, given that we know that the first card is a red. Okay, so to begin with, the probability of a red, half the deck is red, right? So you could say 26 out of 52, or you could say 1/2. Now, when we say without replacement, that means I drew my first card and it is laying on the table in front of me. I do not put it back in the deck before I draw my second card. So when I go to draw my second card, there are only 51 possibilities. So we want to find the probability of drawing a spade since I know that there's already a red card laying on the table. Well, spades are black, so I still have all 13 of my spades to choose from, and so that would be 13 out of 51. So 26 out of 52 is 1/2, so 1/2 times 13 over 51 is going to give me 13 over 102. Now, those two things are called dependent. They're dependent when this given changes this probability. That fact that we were working with a red card changed the denominator on the probability of a spade. So they were dependent on each other. All right, but look at the next one. We're going to do the exact same thing, only this time we're going to do with replacement. And what that means is I draw one card and then I put it back in the deck. I replace it before I draw the second card. So our formula is the same, the probability of red times the probability of a spade, given my first card was a red. Okay, so probability of red is still going to be 26 out of 52, or 1/2. But over here, when we find this probability, because it's with replacement, that means I took that card that I just pulled out and I put it back in the deck before I draw the second card. So when we're saying what's the probability of a spade, given the fact the first card was red, it's completely irrelevant what the first card was because I already put it back in the deck. So I have all 52 cards to choose from, and 13 of them are going to be a spade. So if we simplify that, that's going to be 1/2 times 1/4. So 1/2 times 1/4 would give us 1/8. And those two probabilities would be independent of each other because the first probability did not change the second one. Another way to see that is that if you do the probability of S and the probability of S given R, they're going to be the same thing. So that shows you that this given statement right here is not affecting it at all, that S is completely independent of the R. All right, look at the next one. It says find the probability of drawing a red 6 from a deck of cards. All right, so in my deck of cards, again, I have 52 cards to choose from, but it says that it wants me to draw a red 6. So that's the same thing as drawing a red and a 6. That's going to be the probability of a red times the probability of a 6, given that it's got to be a red. This is not two separate cards here. You can see I'm just drawing one single card here. Okay, so to begin with, the probability of red is half the deck. It's 26 out of 52. And then for the second probability, it says, what's the probability of drawing a 6 if you know the card has to be red? Okay, well, how many red 6s are there in the deck? There's only 2, right? Because that would be the 6 of hearts and the 6 of diamonds, right? Okay, so let's simplify this down. So our 26s would drop out, and 2 and 56 would simplify down. 2 and 52 would simplify down to 1 over 26, and so that would be our probability. Now, you can also use common sense with this if you'd rather. Like, if you think of a whole deck of cards and you think about what are your red 6s, well, there's a 6 of hearts and there's a 6 of diamonds. So there are 2 cards out of the whole deck of 52, and that would give you 1 out of 26. So you can see whether you use the formula or you use common sense, you're going to get the same answer. All right, look at the next one. So the next one is the complement of an event, and we write the complement with a prime mark after it or apostrophe after it, and the complement literally just means not E. So, for instance, if there is a 60% chance of raining today, what's the chance of it not raining? 40%, right? How'd we get that? We did 1 minus 60%. So the complement of it raining is it not raining. So again, you can see if I do 1 minus the probability of the event, then that would give me the probability of not the event, the probability of the complement. So if the baseball team has a chance of 0.9 or 90% of winning the game, what's the probability of them losing the game? Well, common sense, we could say it's just 10%, but if you'd rather use a formula, we could say 1 minus 0.9, so 1 minus 0.9 is going to be 0.1. Now, if you do 90% and 10%, that's fine. Just remember that we always write our probability as a decimal or a fraction. It has to be a number between 0 and 1. All right, look at the next one. If 2 6-sided die are rolled, what's the probability that the sum of the numbers rolled is less than or equal to 3? Okay, first off, I need to come up with my denominator. So I'm going to use my fundamental counting principle from section 13.5. We've got 2 different die here. So the first one can land how many ways? Well, it can land 6 ways. And the second one can land how many ways? It can land 6 ways. So according to the fundamental counting principle, I multiply these two, and there are 36 total possibilities. So that's going to be my sample space. That's going to be my denominator. All right. Out of that, it says how many sums are less than or equal to 3. Okay, so we're rolling 2 of them, right? So if we're talking about how do we get a sum less than or equal to 3, well, let's start with 1. It could be 1 and 1. It could be 1 and 2. All right, then go to 2. It could be 2 and 1, but that's it, right? And that's all that I get that are less than or equal to 3. So it's just going to be 3 out of those 36, or 1/12. All right, then they said find the probability of getting a sum that is greater than 3. Okay, so what kind of numbers are greater than 3? Well, 4. So I could go through and find all the possibilities for 4. That could be 1 and 3, 3 and 1, 2 and 2. And then I could do 5. That'd be 1 and 4, 2 and 3, 3 and 2, 4 and 1. And then I could do 6, and I could do 7, and I could do 8, and 9, and 10, and 11, and 12. There is a better way to do that, right? Okay, if less than or equal to 3, if there were only 3 numbers that were less than or equal to 3 out of the 36, then how many of them have to be greater than 3? The other 33 of them, right? So instead, we could just use our complement and say if I want to know how many are greater than 3, then it would just be 1 minus the probability that they're not greater than 3, that they're less than or equal to it, and there were 3 of those. So we could say 36 over 36 minus 3 over 6, 3 over 36, and that would give us 33 over 36, which we could reduce to be 11/12. All right, look at example 7. Example 7 says the child randomly selects 5 toys from a bin containing 3 bunnies, 5 dogs, and 6 bears. Find the probability that only bears are chosen. Okay, so for my denominator, I have 3 plus 5 plus 6. I have 14 things to choose from, and out of those 14, I'm choosing 5, right? I'm selecting 5 toys. Okay, so in my numerator, it says, what's the chance that I only get bears? Well, there are 6 bears to choose from, and so for the 6 bears, I'm choosing 5. And these are those combinations that we were doing before. You could do them by hand or on your calculator, either one. All right, look at this one, the probability that you have 2 bears and 3 dogs. So our denominator is still going to be the same. It's going to be 14C5. But for 2 bears, there are 6 bears to choose from, and we're choosing 2. And there are 5